the and dimension, so it can be written as x1, x2, and xn are the components of this vector x. Is the optimization variable. Optimization variable of the problem. Okay, and your function, objective function, is basically mapping from Rn to R. So this is a mapping from Rn to R, and this f naught x is known as the objective function. This is the objective function, and the rest functions are fi, and these functions are functions fi. This is also from R into R, and here is all f1, f2 up to fm are the inequality constants. Okay, so these are the constants are you call this is inequality constants. This is inequality constants. Okay, so here you have to find the inverse problem. So you have to find what are the value of x, that is x star, and that expresses your optimal solution. Okay, so the vector, and that vector if we call x star, this is called optimal solution of your problem, or in other words you can say the solution of the problem, or a solution of the problem that is defined by equation number 1. Okay, if this is solution when it has the smallest value, because this is problem of minimization. So if it has the smallest,
तो
yes,
इनइक्वालिटी के साथ क्या लिखे हैं आप कॉन्स्टेंट क्या
कहाँ पे
इनइक्वालिटीज ब्रैकेट के बाद
inequality constants, inequality constants, and a vector x star is called optimal or solution of the problem equation 1 if it has the smallest objective value among all the vectors, among all vectors that satisfies the constants. Okay, so this means if any z, so for any z with the objective value is f naught, this f1 inequality constant. So f1z is less or equals to suppose b1, f2z suppose less or equals to b2, and suppose the last one inequality constant is fn z. This is less or equals to bm. So we have this f naught z. If you find any z, so this value is greater or equals to your the optimum one. Optimum one is your x star. So this is your objective function at this thing. Okay, this means x star is the optimal solution. Okay, and this linear, this optimization problem is said to be linear programming problem if our objective and constants functions are linear. Okay, so here you can say that ever optimization problem that is equation number 1 is called a linear programming if the objective function, constant function, that is and constants are f1, f2 to fn, all are linear functions. Okay, so linear function means that is when we say that these functions are linear, this means that is this satisfy this equation. That equation is for any alpha x plus beta y, this equals to alpha of fi x plus beta of fi y. Okay, so this is suppose equation number 2, and this holds for all xy that belongs to Rn, and here alpha beta are the scalar any real number r. Okay, so this is the condition for the linear programming problem. Okay, so now if the optimization problem is if this is not linear, these functions are not linear, then we call this is a non-linear programming. Okay, so okay, so here you can write down if the optimization problem is not linear, if the optimization problem is not linear, not linear, then it is called then it is called non-linear programming problem. So this is non-linear programming problem. Okay, so if this is linear one, you say that this is a linear programming problem. Otherwise, this is non-linear programming problem. Okay, so if there are certain more conditions, so in next page, next page. So if our objective function and constants are the objective constants functions, constant functions, these are convex functions. Okay, convex function means satisfy this relation. You know that what are the relations beta y. So this is less or equals to alpha time plus beta times phi of y. Okay, here the conditions are, what is the conditions between this is scalar one or okay. So now 3. So that type of relation is satisfied. You know, it's called convex optimization problem. So this is called optimization problem. which is a generalization of linear programming problem. So finally, you see that your convex optimization problem is more general than your linear programming problem, and of course for non-linear programming. Okay, types of programming problems. So we only write here what are the certain types of problems. So first one is least square problem. Okay, so here we deal some examples of here least squares problem. So least square problem is defined as a least square problem is this is a optimization problem. This is optimization problem where there are no number of inequality constants. Okay, so with no constants, the no constant means here n equals to zero basically. Okay, n of the function of the form and the objective function objective function which is a sum of squares of terms of the form squares of terms of the form uh, this is ai transpose x minus bi. Okay, so here this is categorized into the least square problem, that is minimize your objective function, and objective function is defined as this type of norm of some ax minus b. Okay, so this type of problem, or you can type in this form I equals to 1 to k I transpose x minus bi, and that is square. Basically, this is a sum of square terms. Okay, so this is a equation of matrix A is basically a matrix of order some k cross n, and here your ai transpose, these are the basically row of these are the row of matrix A. Okay, this is rows of matrix A, and this your vector x is basically belongs to Rn. And here this dimension is k cross n, and here of course k is greater or equals to n. Okay, so or you can write m cross n to m. So this is the type of least square problem. Okay, so this is the simple type of optimization problem where you have to find the least square sum. Okay, so here the minimization of type of problem where the no constants are given. Okay, so this type of problem is categorized into least square problem. Then next to is linear programming problem. Okay, where and also the constants are given. Okay, so the next one is linear. Okay, so this is a Another important class of optimization problem in which the objective and all constants are linear. Okay, so here and constants are constant functions are linear one. Okay, so okay, and subject to the constants, with the constants are ai x aix that equals to something bi. Okay, and here the I is varies from 1 to n. This second type of equation, and here what is the vectors? The vectors that is c a1 a2 all are belongs to or an that belongs to rn. Okay, and the scalar one and scalars are b1 b2 up to bm. So these scalars are b1 b2 up to bm that are scalar one. So this belongs to rn because this is scalar one. Okay, so here these are the basically the parameters of the problem and satisfy the objective and constant function. Okay, and another type of problem is a convex optimization problem. So here, this type of problem is defined as minimize your objective function, that is f naught x, and subject to constants are fix. This is less or equals to pi, where I is varies from 1 to m. Okay, there are some inequality constants and also equality constants, and to know that all the functions are this objective functions and this quality constants f1 f2 up to fm, these are mapping from rn to r, and all are basically convex function. All are convex functions. Okay, and all functions satisfy the certain condition, and that condition is fi of alpha x plus beta y that equals to alpha of fix plus beta of fiy, with this alpha plus beta equals to 1, and all xy belongs to rn, and this alpha beta belongs to scalar one, that is r, with certain condition this sum equals to 1 and all are non-negative. Okay. So these are the conditions. Okay, here you know that the least square problem. So the least square problem, first equation 1, the least square problem, that is equation 1, and the linear programming problem, that is equation number 2. These are both are special cases of are both special cases of this general convex optimization problem. optimization problem that is defined in equation number 3. Okay, so you can see that this is a general optimization problem, and for this method you can solve your linear programming problem as well as your least square programming problem. Okay, and for non-linear program problem, which are non-linear program, so basically this non-linear programming optimization problem is a term used to describe an optimization problem when the objective or constant problems are non-linear. Anyway, if the objective is non-linear function, then you say that your problem is non-linear programming. Or if any constants is non-linear function, then you see that your optimization problem is non-linear programming problem. Okay, but that non-linear programming problem is also known as to be convex programming problem if that programming problem it satisfies this certain rule. Okay, and in fact there are no effective method for solving the general non-linear programming problem. So there are the certain methods for different type of general non-linear programming problem. So therefore there are several different approaches, each for which we have to some compromise for solving that type of problem. Okay, so in our next lecture, we will see some types of non-linear programming and also how to solve the random optimization problem. Okay, when our this objective function is mapping from Rn to R, when this mapping is objective function is Rn to Rm. Okay, so there are n number of objective functions, so we have to minimize all these things. Or some problem we have to minimize, or some we have to maximize. That type of problem is categorized into the vector optimization problem. Okay, so we will go through that type of problem and solve that type of problem also. Okay, so here these are certain definitions of mathematical optimization problem, and here we try to uh, relate and try to show that our Corners optimization problem is the most general optimization problem amongst all that linear or non-linear or least square optimization problem. Okay, so in future we will try to solve and what are the techniques for solving that type of linear programming problem and Corners optimization type programming problem. Okay. So now we go through the next topic. And before that, for global minimum and global maximum, so here we deal some small theorem, okay, and which is based on our yesterday class, and where we have used some corners optimization problem, and we use a formula. That formula is 2 minus that is equals to your gradient of fx1 transpose x2 minus x1. Okay, so yesterday we have already solved that type of theorems, and we have some problem on based on local and global optima, and for that we will solve and we will prove that how our local optimal solution for convex function is also the globally optimal solution. Okay, so before that we take a small theory, okay, which is based on the study class. So next page, take a small theorem. This theorem says that if your function is principal function, if f is uh, differentiable convex function, if f is differentiable, if is differentiable convex function, Okay, so if f is differentiable convex function on convex set C in Rn, and if you take a point which is belonging to that convex set C, then you have to prove that this f of x naught, this value is a global minimum of the function fx. If and only if we satisfy certain condition, and that condition is gradient at that point, that is your global minimum point, this transpose x minus x naught for any x belongs to your convex set C, this is always greater than or equals to 0 for all x that belongs to convex set C. Okay, so proof.
सर यहाँ ग्लोबल मिनिमम का सेंस क्या होगा?
Global minimum means if you any function, suppose there is suppose this type of function. Okay, so here there is a some minimum is here, some minimum is here, some minimum is here. Okay, and you can find any minimum in any interval. Suppose that type of interval, and that set is your convex. Okay, so this minimum is also your means if this x which belongs to that set C, if you contain that convex set C, so this is also minimum of that. If you contain that C, so you have the same point is your minimum of this function. Okay, so here ग्लोबल मिनिमम का सेंस यही है कि जो आपका अगर फंक्शन कॉन्वेक्स है, अगर फंक्शन आपके कॉन्वेक्स है, तो जो लोकल मिनिमम होंगे वही आपके ग्लोबल मिनिमम भी होंगे. इफ यू टेक सपोज एनी फंक्शन इन वन डायमेंशन Rn, और आपने एक इस तरह की अगर आपने कॉन्वेक्स फंक्शन का आपने लिख लिया, ओके, जिस फंक्शन में आपका ये जो मिनिमा होगा, ये मिनिमम होगा, ये आपका मिनिमा इन ग्लोबल सेंस होगा फॉर ऑल दिस R. Okay, and if you take your x belongs to Rn, for x belongs to whole domain Rn, your that minimum is also the global minimum. Okay, and if your function is suppose not convex means suppose this type of function is suppose this type of function is here, and you take any local minima is here. If you take that interval is C with let's C, okay, and your function is not convex in this whole domain. Okay, so this minimum is not your global minimum, because the global minimum is this point, because this is also a point which is the minimum of that value. Okay, here if your function is your convex function, then your minima, the local minima, is your global minimum. So here we try to find for our convex function, we try to find our local minima, and that local minima is also our global minimum. Okay, so here we try to prove that this, if our this function is differentiable function, okay, and here we put that this condition is satisfied. If this condition is satisfied for all x that belong in any convex set C, then our x naught is our minimum value. Okay, in that set basically. Okay, here you can only say that this at point x naught, for all x belongs to C, x naught is the minimum value for all x which belongs to that set C. Okay, so here the concept of global minimum is basically that this fx naught is less than less or equals to for any z that z belongs to that set C. Okay, so here we suppose that this condition hold, and that condition is gradient of f of x naught transpose x minus x naught. this is greater or equals to 0. If this condition hold, so we have to prove that this fx naught value is always less or equals to for any value of x, function of x at uh, in this domain. Okay, so if this condition holds for all x that belongs to convex at C, and you know that your function is convex. The main point is function should be convex. So this is convex. So you know that by yesterday class. So we here by previous theorem, and that theorem uh, you have fx2 minus fx1, that is greater or equals to gradient of fx1 transpose x2 minus x1. Okay, so yesterday we have uh, proved this condition. Okay, so we had proved this condition. So now we can write here for any x minus x naught, this is greater or equals to we x minus x naught. Okay. And here this condition holds gradient of x naught. This this thing. So this implies your fx minus fx naught. This is greater or equals to 0, or you can see that this x naught is less or equals to f for all x that belongs to convex at C. Okay, so this means is always less or equals to this function value at any x which belongs to convex at C. This fx naught is proof. We suppose that we take any, then for all x this condition holds. Okay, because this is global minimum. And 1 minus theta of this x and x in convex function, their local minima hai, that is also your global minima. Okay. Is also globally optimal. Okay, so this is the fundamental property of your convex optimization problem. Okay, so if you try to see that this is the if You see this. Okay, so we have to suppose that if x is locally optimal for a convex optimization problem, convex optimization problem, that is x is feasible and your objective functional value, that is f naught x, this equals to the minimum value, that is infimum of this functional value, this is the infimum of f naught objective function, such that z is feasible and also satisfies the condition. That condition is in this feasible region. Okay, so suppose this is your equation start, and here this thing. So now suppose that if we suppose that,
सर
yes,
सर ये आपने एफ नॉट ऑफ एक्स इज इक्वल्स टू क्या लिखा है?
infimum of, because our problem is a minimization problem, so this is infimum INF,
ओके
infimum of this f naught z, where z is feasible, and this defined in certain reason, that is z minus x if less or equals to r, where r is greater than 0. That is your feasible reason. Okay, so now our claim is that if we suppose that our x is not global minimum. Okay, here we take x is locally optimal. So if we take x is not globally optimal, it's not globally optimal. So that is, there is any another feasible solution, which is if we take this, that is a y. So if there is a feasible y such that the value of this f naught y, this one is the global minimum, so this is less than your this local minimum. So you suppose that thing. Okay, so evidently your norm of this y minus x, because this is greater than r. Okay, so here if we otherwise your f naught x is less or equals to f naught y, because if this condition is satisfied, then y minus x, then this is your infimum. So here this is less or equals to r. This means you get any other y which is not your locally minimum. So that y belongs to the other than this domain, and that domain is norm of y minus x is greater than r. Okay, so here if we consider the point, if we consider the point, any point that is z, which is given by a convex combination of x and y. So this is 1 minus theta x plus theta y, and we take theta is basically r over 2 norm of y minus x, because here you know that and here this norm of y minus x is greater than r, norm of y minus x greater than r, and r is of course greater than 0. If we dividing this by norm of okay, if we dividing by this 1 by 2, you can write here 1 by 2 is greater than r over norm of y minus x by 2. This is greater than 0 because if we dividing norm of this two side and by 2. So this term is equals to this thing. So here theta is basically equals to r over this thing. So your theta is lies between 0 and 1 and of course greater than 0 if we take theta equals to that value. Okay. So here no problem because so theta is greater than 0 if we take this value is theta. Okay, so this theta is greater than 0 and lies between 0 and 1. So we take this theta. Okay, so now this equals to norm of what is the value of f. Then we have and the what is the value of norm of z minus x. Okay, so this value is norm of z. Z means 1 minus theta of x plus theta of y. This is the value of z minus x norm of this. Okay, so this equals to if we try to solve this equals to theta and 1 minus z to x are cancelled out and here minus theta x plus theta x. So here theta times y minus x. So here theta with the scalar one, so you can write theta into norm of y minus x. And what is the value of theta here? So theta is this is basically theta is equals to this thing. So you can write here r over 2 norm of y minus x and here norm of y minus x. Okay, so this equals to r by 2 and this r by 2 is of course less than our r. Okay, so this means this z minus r x is less than r equals to this r. Okay, so and by the convexity of the physical set, your z is basically feasible. Okay, because this lies between this interval, so z is feasible. Okay, so by convexity of function f naught, we have what is the value of f naught z. So this equals to f naught. What is the value of z is? That is 1 minus theta of x plus theta of y. Okay. So this is lesser equals to by the convex function. You know that 1 minus theta of fx plus theta of fy. Now objective function is f naught and here f naught of y. Okay, so this equals to f naught of x plus theta if we take theta together. So this means f naught of y minus f naught of x. Okay, so here you know that this theta is greater than 0 and f naught y and minus f naught x. Okay, so f naught y here you assume that you this f naught y is because is greater than f naught x. Okay, so here this term is greater than 0. This term is greater than 0. Okay, and theta is greater than 0. And this term f naught y minus f naught x, if you try to relate that term, so here you get what is the value of f naught y minus f naught x. So f naught y minus f naught x, this is less than 0. This term is less than 0, this is negative 1. Okay, so this term is less than 0 and here theta is greater than 0. This theta is greater than 0. The product of this is negative 1. Okay, negative 1. So if we eliminate this negative term, so this term is of course f naught x. That term is write down this is f naught of x because here you neglect this negative term. Okay, so if negative term is removed from that, so this term is remaining term is greater than. Okay, so that is greater than f naught x. Okay, so this implies finally f naught z is less than f naught x. Okay, so this means f naught x. So there exists no feasible y with f naught x is less than f naught x, that is x is globally, okay, optimal. Okay, this means x is your globally optimal solution. Okay, so now it is not true that locally optimal points of quasi-convex optimization problem are globally optimal solution. Okay, so this is only true for your function is convex. So for any convex function, your local optimal solution is also the global optimal solution, and that is the fundamental property of your convex optimization problem. Okay, but if your problem is suppose your quasi-convex type of problem, so in that case your local optimum is and is not equals to your global optimum. Okay, so okay, so ठीक है, तो अभी आज के लिए इतना ही करते हैं। ठीक है, 2 क्लास है लेकिन नेटवर्क की थोड़ी सी प्रॉब्लम आ रही है। आज इतना ही करते हैं। नेक्स्ट क्लास हम नेक्स्ट वीक से करेंगे। ओके।
हेलो सर।
हाँ, हाँ।
फिर एग्जाम फॉर्म की लास्ट डेट कब है?
किस चीज़ की?
एग्जाम फॉर्म फिलअप करनी है, वहाँ जो सेम कोर्स है ना वो तो लास्ट जुलाई में स्टार्ट होगा, तो फिर अभी हम लोग का सेकेंड सेमेस्टर में।
ओके, ओके। उसके लिए थोड़ा जो कोर्स कोऑर्डिनेटर है ना वेंकटेश तिवारी जी, थोड़ा उनसे पूछ लीजिए। और वहाँ पे एक प्रियंका है ऑफिस में, अभी तो कोई आ भी नहीं रहे हैं, तो आप उनसे उन्हीं लोगों के पास अपडेट होंगे, कोर्स कोऑर्डिनेटर के पास। कोर्स कोऑर्डिनेटर के पास अपडेट होंगे और हमारी सजेशन यही है कि जो भी आपको स्वयं में जो दिख रहे हैं कोर्सेज जो रनिंग है उनको आप ले लें। उसमें कोई इशू नहीं है कि वो अभी
जुलाई में जो भी कोर्सेज है ना वो लास्ट जुलाई में स्टार्ट होंगे।
कोई बात नहीं, तो होने दीजिए, आप उसको करके फिर आप उसको सबमिट कर देना, कोई प्रॉब्लम नहीं, कोई प्रॉब्लम नहीं। अगर अभी अभी किसी में एनरोलमेंट हो रहा हो तो आप उसको ऑप्ट कर लें, किसी ने पहले से कर रखा हो तो बहुत ही अच्छा है, किसी ने अगर नहीं कर रखा है तो जुलाई में ले लें, वो जुलाई में आप चाहें तो 2-2 ले सकते हैं। आप कोई भी 2-3 कुछ भी ले सकते हैं, एक भी ले सकते हैं, जिसमें भी आप क्लियर कर लें उसके सर्टिफिकेट आपको हमारे ऑफिस में सबमिट करने होंगे। ठीक है, जब अभी अभी किसी में अगर इनरोलमेंट नहीं हो रहे हैं तो आप कैसे कर पाओगे, तो नहीं करोगे। जिन्होंने कर रखा है पहले से वो बिल्कुल करें।
सर हर सेमेस्टर के अभी से हम लोग स्वयं कोर्स में इनरोल कर सकते हैं?
क्या क्या क्या
तो
करें?
थर्ड सेमेस्टर में भी हम लोग का स्वयं कोर्स है सर, अगर हम 2
हाँ,
कोर्स स्वयं का इधर
स्वयं में भी
लेंगे।
है, स्वयं स्वयं थर्ड सेमेस्टर में भी है, थर्ड जो है स्वयं में भी है। लेकिन ऐसा नहीं कि अभी आपने 2 कर लिया और फिर थर्ड में ना करें, फिर कहें कि नहीं नहीं मेरा यही वाला उसमें ले लीजिए, ऐसा नहीं है। तो आप एक से ज़्यादा ले सकते हो, एक से ज़्यादा आप ले सकते हो, और आप किसी का भी मार्क्स, जिसके भी मार्क्स आपके ज़्यादा आ रहे हैं उसको आप सबमिट कर सकते हो। ये आपकी अपनी चॉइस है, आप चाहे तो 1 लीजिए, चाहे तो आप 4 लीजिए, पर आपको एक ही जो है हमें ऑफिस में सबमिट करना है। अब बात ये है कि किसी
सर बट एग्जाम फॉर्म में तो एक ही चूज करना है ना।
सर एग्जामिनेशन फॉर्म में तो हमें कोई एक ही सेलेक्ट करके वहाँ भरना पड़ेगा ना।
हाँ हाँ बिल्कुल बिल्कुल करना पड़ेगा, लेकिन अगर किसी ने अगर ऐसा नहीं कर पाया है या ऐसा स्वयं का कोर्स है जो उसकी उस लिस्ट में नहीं है, तो वो उसको एप्लीकेशन लिख करके उसको सर्टिफिकेट लगा देगा तो उसका चेंज हो जाता है। ऐसी बहुत बड़ी इशू नहीं है ये, ठीक है। लेकिन इस पे भी एक बार आप जो है अपने कोर्स कोऑर्डिनेटर से एक बार बात कर लें, और जो प्रियंका मैडम है जो आपकी ऑफिस असिस्टेंट है मैथमेटिक्स कंप्यूटिंग की, उनसे बात कर लें और क्लियर कर लें। हमारे पास जितनी नॉलेज है हम उसमें आपको बता रहे हैं कि आपके पास अगर उस पोर्टल पे अगर वो ड्रॉप डाउन में नहीं आ रहे हैं कोर्स, तो कोई एक चूज कर लीजिए। और आपने अगर कोई स्वयं में कोई और भी अगर आपने कर रखा है तो उसको एक एप्लीकेशन दे करके आप उसको चेंज करा सकते हैं। लेकिन कुछ स्टूडेंट चाहे तो ऐसा करते हैं। आप सभी सभी ये मत करने लगना कि हमने ड्रॉप डाउन में हमने कुछ और सेलेक्ट किया और कोई और पेपर किया, तो कंट्रोलर को भी लगेगा कि ये क्या है, सारे सारे 40 बच्चे एक ही काम कर रहे हैं। तो ऐसा नहीं, इमरजेंसी में आप ऐसा कुछ कर सकते हो। और अदरवाइज अगर आपके ड्रॉप डाउन पे अगर वो मिल रहे हैं कोर्सेज, आपको वो कोर्सेज ओपन भी हैं, आप बिल्कुल आप उसको करिए। लेकिन किसी कारण से कोई बच्चा अगर वो ले लेता है, अगर उसमें क्लियर नहीं कर पाता और दूसरा कोर्स अगर वो क्लियर कर लेता है, तो उसको वो लगा सकता है, उसका वो चेंज हो जाता है। ठीक है, मेरा इतना कहना है। और सभी लोग ये काम मत करने लगना। हाँ, इसके लिए आप पोस्ट पॉइंटर से एक बार बात कर लीजिए कि हम क्या करें। ठीक है, वो आपको जैसा कहें वैसा करिए, क्योंकि मेन कंसर्न इसमें पोस्ट पॉइंटर की होती है। पोस्ट पॉइंटर और ऑफिस में जो भी सारी इंफॉर्मेशन है उन्हीं के पास होती है। हम तो पिछले एक्सपीरियंस के हिसाब से हम आपको बता दें कि ऐसा भी होता चला आया है यूनिवर्सिटी में। ठीक है, ओके। तो आज इतना ही करते हैं, नेक्स्ट क्लास फिर अगले दिन करेंगे। घर से थोड़ा सा नेटवर्क इशू है, तो बहुत ज़्यादा नहीं चल पा रहा है, फिर भी कोशिश करते हैं। ठीक है, तो अगली क्लास अब थर्सडे को होगी, नेक्स्ट थर्सडे। ओके,
थैंक यू सर।
थैंक यू।
थैंक यू सर।
थैंक यू सर।